Hi, I'm Shalev Kuba, a master student at the Technion, and today I'm presenting Leaded Slide, Online Deduplicated Data Migration, a joint work with my advisor, Gala Yadgar. We'll start with a quick reminder. Deduplication is a common technique in storage systems that saves space by keeping a single copy of duplicate blocks. Many systems apply it per volume rather than globally, so identical data is deduplicated only within a volume. In each volume, files hold logical references to unique blocks. Here, for example, blocks B1 and B2 are stored once in volume 1 and referenced by both file 1 and file 2. In our data migration model, migration moves files and their blocks across volumes. This process typically occurs during maintenance, recovery, resizing, etc. In deduplicated systems, migration is tricky. Each transfer may cause blocks to be deleted, replicated, or moved, which may increase or decrease total system size. For example, if we transfer file 2 to volume 2, block B1 is replicated, as it's still needed on volume 1, but doesn't exist on volume 2. Block B3 is deleted, as it already exists on volume 2 and is no longer referenced on volume 1. And block B4 is moved, as it doesn't exist on volume 2 and has no other references on volume 1. In this work, we address online migration, where migration runs while system continues to serve users, so system state keeps changing as users add and delete files. New files may add references to a block and prevent its removal. Deletions may leave blocks with no references, allowing them to be deleted and potentially preventing future transfers from reusing those blocks. Also, migration may affect system performance by consuming significant bandwidth, causing traffic spikes, or overloading specific volumes. Unreferenced blocks are removed only by garbage collection, GC. In production, it typically runs about once a week because it's expensive computational cost. In this example, blocks B3 and B4 are reclaimed in the GC run as they are not referenced by any file. We call the interval between two garbage collection runs a GC epoch, or in short, an epoch. So what are the goals of deduplicated migration? Prior work by Kistos et al. Defined the migration plan as a list of file-to-destination transfers. A goal of such a plan is to minimize final system size under constraints on total network traffic and balance of the final state. Kistos et al. Also presented migration algorithms that receive the initial state and the constraints and output a migration plan. However, these algorithms are offline and consider only the initial and final states and the total data transferred. They do not address the process itself, such as order of transfers, resulting intermediate states, garbage collection, or changes that may occur in the system while the migration is running. As we are the first to address this online variant of the problem, we had to formalize it first. We did that by extending the offline formulation to reflect these online challenges. First, we define a migration window as a number of consecutive GC epochs allocated to the migration. The per epoch sequence of file additions and deletions is unknown in advance. Our goal is to compute an online migration plan, which is a list of per epoch migration plans. We preserve the previously defined offline goals of such a plan and add two additional goals as an online extension. First, to minimize per epoch traffic, and second, to maximize the balance of intermediate states across the migration window. Now, we will present the online migration algorithm in this work using a simple example. All these algorithms use an offline migration algorithm, but they differ in the way they use it, as will be discussed soon. For full definitions, see the paper. Consider the following system state and these migration settings. A migration window that consists of two GC epochs, an allocated traffic budget of 2 blocks, 1 block per epoch, and the balance constraint of 1 block, meaning difference in volume size can be more than 1 block. In these initial states, there are 8 physical blocks in total. The balance metric is defined as the smallest volume size divided by the largest, which here equals 1, a perfectly balanced state. The first online algorithm we present is space split. This algorithm constructs a window-wide plan during the first epoch using the offline migration algorithm. Then, it greedily splits that plan to epochs. In this example, the resulting window-wide migration plan has 2 transfers, file 1 to volume 2 and file 3 to volume 1, which together reduce system size by 1 block at the cost of transferring 2 blocks. In each epoch, it executes subset of these migration transfers as long as there is enough traffic budget, prioritizing space reduction. So in the first epoch, space splits first transfer file 3 to volume 1, yielding a reduced size but imbalanced intermediate states. After garbage collection, the unreferenced block B2 on volume 2 is reclaimed, so in the second epoch, the transfer of file 1 to volume 2 now costs 2 blocks, exceeding the epoch's budget, so it is discarded and the system is stuck in the same imbalanced state. The second online algorithm we present is balance split. This algorithm constructs an offline migration plan for a window similar to space split. In contrast to space split, it prioritizes balance. Hence, in the first epoch, it executes the transfer of file 1 to volume 2. In the second epoch, it is still possible to continue and execute the transfer of file 3 to volume 1 at the cost of another block, reaching the desired final state. In this example, it didn't get stuck like space split, but it may also get stuck and yield worse results. For example, let's say that a user adds a new file, calls file 5 identical to file 3 to volume 2 during the first epoch. In that case, balance split will not move file 5 during the second epoch, causing the system size to increase by 1 block. The full example appears in the paper. Last but not least, we present Slide, our novel online algorithm. Slide constructs a window-wide plan using the offline migration algorithm in each epoch. In this example, in the first epoch, the resulting plan is similar to the one of the split algorithms. Similar to balance split, within an epoch it prioritizes transfers by balance, hence, in the first epoch it executes the transfer of file 1 to volume 2. In the second epoch it reconstructs another window-wide plan, meaning the window slides, and the resulting plan continues the original plan, yielding a single transfer, file 3 to volume 1. Slides then executes that transfers, yielding, in that specific case, the same desired state as balance split. That's not always the case, as will be seen soon in the results. In particular, in contrast to balance split, if file 5 is added by the user to volume 2 during the first epoch, Slide would choose to transfer this file along with file 3 to volume 1 as it reconstructs the plan at the start of the second epoch. To evaluate the different online algorithms, we built a system based on the UBC datasets with each user's files initially placed on a single volume. For additions and deletions, we simulate a backup stream, where in each epoch a random subset of users add a new backup and remove their oldest. The paper includes results on additional systems and change patterns options. Now, let's go over the result of our basic comparison. For completeness, we include the following baseline algorithms. See paper for their full definitions. None, which means no migration, only system changes. Pre computes a window-wide plan in the first epoch of a window and executes all transfers in that epoch, ignoring per-epoch budgets. Post computes a window-wide plan similar to pre, but executes all transfers in the last epoch of that window. Multiple migration computes migration plan in each epoch using epoch's budget. We report the following metrics, where metric result on the first row is shown as a percentages of initial system size. Max traffic is the highest per epoch traffic observed across the window. Increase in system size is the net size increase after the migration and the system changes ends. Max volume size is the largest volume size observed across all epochs. Final balance is the system balance at the end of the migration, and minimum balance is the lowest balance observed at the end of an epoch across the migration. The results show that pre and post cause large traffic spikes as expected and can be seen in the max traffic graph. Space split yields highly imbalanced intermediate states as can be seen in the minimum balance graph. Slides achieve the best balance as can be seen both in final and minimum balance graphs. Slide also shows comparable size increase to other approaches, as can be seen in the increase in system size graph. Here, we show the same experiment in a per-epoch view. As expected, pre and post produce high traffic spikes in the first and the last epoch, respectively. Post yields the highest max volume size because it executes migration only in the final epoch of a window. Space split starts highly unbalanced, improves gradually but ends up with the lowest final balance. Slides quickly stabilizes the systems and maintains that advantage across all epochs. More experiments covering different systems, change streams, change rates, and more appear in the paper. To conclude, the experiments show that to achieve balanced intermediate states, a migration algorithm should address it explicitly. Also, to prevent traffic spikes and performance degradation, a per-epoch traffic limitation is necessary. And most importantly, the results show that slides adapt effectively to changes and delivers the best long-term short-term trade-off across varying conditions. The paper also shows that slides runtime overhead scales linearly with the number of epochs. Lastly, slide is modular and can be extended, by example, by swapping the offline migration algorithm or adjusting the per-epoch execution order to target additional goals, like prioritizing hot files or high reliability. We leave such extensions for future work. All the source code for this research available on GitHub. Thank you.